So if we're trying to keep pace of what we've been doing, we've been discussing, and what these are, as I've said before, I keep yapping about it. We've been discussing theorems, but I'd like to think of these as rules or shortcuts for efficiently computing derivatives. So, for example, last class, we discussed a few things that are important. So, we discussed the product rule, the quotient rule, and some important formulas or important identities. So let's list these roles, because they're things that excuse me, I'm all clogged up. These are things that you got to know how to do. They're just fundamental to this course. So, for example, we have this formula that the product of two functions, if we want to compute its derivative, the product rule says that we can compute it like this. So I'm writing this in shorthand, and hopefully you make the connection with what we did last class with slightly different notation. This is called the product rule. And then a closely related rule or formula is if I want to compute the derivative of a quotient, it's done like this. So this is called the quotient rule. And then we also, we proved a very important identity, and that is that the derivative of sine is the cosine. And then a similar argument would prove that the cosine's derivative is negative the sine. And using these four formulas, these four identities, we can derive all kinds of derivatives now. We also mentioned this very important rule about the exponential function, that e to a number times x, the derivative is ae to that number times x. So these are five very, very important formulas that you should have memorized, and hopefully you already do. Now, I'm not assuming you do, but I'm using that to motivate you. You need to know these things. We will use them over and over and over again. Excuse me. So it's important that we do some examples to help illustrate these guys. Does anybody have a question about anything you see on the whiteboard right now? Okay, so sweet. So what you should do is you should verify the following. You should verify that the derivative of, say, the tangent is the secant squared, you should verify, although we did this in class, I believe, that the derivative of the secant, I think we did this, is secant x times tan x. And then while we're at it, I guess you should even verify that the derivative of the cosecant is negative the cosecant times the cotangent. And then last but not least, the derivative of the cotangent is negative the cosecant squared. So you should verify that all these formulas are true, and they're not difficult. All four of these can be verified using the quotient rule. You just write tangent as sine over cosine, you write secant as 1 over cosine, you write cosecant as 1 over the sine, and then you write cotangent as 1 over the tangent. And if you do that, you'll get these, excuse me, you'll get these formulas. So what we're building is we're sort of building up all the functions that we can easily differentiate. So if you have a question or something, please interject. Okay, so once we, and again, let me go back to this. When I say you should verify, you should derive these on your own. That's good practice. You know, it's like if you want to be a good basketball player, you go and you take a basketball and you go to the gym and you shoot the damn ball and you dribble it and you run around and you practice. If you want to be good at softball or baseball, you practice. If you want to be good at math and science, guess what? You practice. That's just what it is. You practice. It's not always enjoyable, but that's how you get good. Okay, so let's do a couple examples that are similar to the homework problem. Or problems, I should say. So suppose, excuse me, suppose I want to differentiate x to the 5th times e to the 23x. So, you know, what I need to do before I do anything is I have to think about what kind of function am I differentiating. And so what I notice is that I have two pieces to this function. I have a power function, x to the 5th, and then I have an exponential function. And so what that tells me is that tells me that I have a product. And so I should differentiate this according to the product rule. And so I will do that very slowly. And again, I mentioned this on Tuesday. Some of you won't need these intermediate steps. Some of you will. So I'm calling this an intermediate step because the answer is then, not the answer, but the derivative. Once we compute these two derivatives, we are left with this. And if you want, you could factor out some common factors like x to the 4th times e to the 23x, and you're left with 5 plus 23x. Now, if this were a homework problem, I would be fine if you left your answer like this. If this were a test question, I would be fine if you left your answers like this. But my personal preference is for myself, if I can easily rewrite an expression in what I deem a simplified version, I'm going to do it. So while the line that has the red check mark is the derivative, I wanted to write it in a little cleaner manner. So that's why I did what I did. Does anybody have a question or a comment about this? Okay. The silence is deafening. Very good. So let's do another one. Let's compute the derivative of the following. So 1 minus the sine of x divided by 1 plus the sine of x. So here I have a quotient. So the first thing I'm going to do is I'm going to apply the quotient rule, which says I take the derivative of the bottom, leave the top alone, minus the top, times the derivative of the bottom, all over the bottom squared. And so if I differentiate these pieces up top, I get the first one's derivative is just cosine times 1 minus sine. Yay, nay. No one yelled at me yet. This is why I hate doing Zooms. I'd much rather be in a classroom. So someone would scream, "You made a mistake." So where's the mistake? The mistake is that we already wrote the formula down incorrectly. So this is a very common error that's going to happen when you write the quotient rule down. You got to make sure you get it correctly from the beginning. So what you'll notice is I wrote the rule down. The rule is not what I've written here. The rule is the bottom times the derivative of the top. So what I should have had is I should have this term being differentiated. Then it's minus the top times the derivative of the bottom all over the bottom squared. So you have to be very careful. And the reason I emphasize this is because with the quotient rule, oftentimes the mistakes aren't with the calculus, it's with the simple understanding of making sure your grouping symbols are in the right place and making sure you take the correct derivative at the correct spot. So again, the quotient rule is bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom square. I guess that's one way to think about it. Okay, so if we're careful now, we leave this guy alone. And then the derivative here becomes minus the cosine. And then the derivative here is just cosine. Now, once again, you are okay if you want to leave it like this. This is, in fact, the derivative. So it's not wrong if you stop here. However, in many applications we're going to do later on, you're going to have to be able to work with this derivative. You're going to have to be able to do things with it. So you might as well start practicing now how to write it in a more usable form. So what I can do is I can, in fact, do some algebra. So this becomes, if I distribute the cosine here, I'm left with negative cosine x minus sine x cosine x. And then this becomes minus the cosine x plus sine x cosine x, because I have this minus sign floating around. And so what you'll notice is a couple of these terms cancel out, and you're left with minus 2 cosine x all over this creature. So you got to double check your work as well. And I can't emphasize that enough either. At every step, you got to say to yourself, okay, does this line make sense compared to the previous line? Does anybody have a question or a concern? So a couple things I should mention, and I mentioned this last week. There is all types of software out there, many of it free, that will take derivatives for you. That wasn't true 5 years ago or 10 years ago, but it is true now. That being said, you are still required to prove that you know how to do this. Even though a calculator will do this for you, you need to be able to do it by hand. That's still part of the curriculum of calculus. So keep that in mind if you're using software to help you. There's nothing wrong with that. I encourage that you use technology. It's a great tool. You got to use it. It helps you learn. But I will also remind you that your goal is to be able to do this on your own. Luckily now you have technology that can help assist you, and it can also be used to verify that you get the correct answer. So I hope that you keep that in mind. I hope you don't just use software to get the answers, because really, if you think about it, that's a big waste of your time. If you spend your whole time just using, sort of the internet and software to get the answers, and you don't take the time to actually learn what you're doing, then you're just wasting your time. You really are. So I would highly encourage that, you use technology, but I also highly encourage that when you use technology, you learn from it. Don't just get the answers. So that's my 2 cents on it. Any questions on this example before we move on? All right, good. So let's move on. Okay, so let's look at another example to help motivate sort of our next big rule. So use green. So suppose we want to differentiate this. 5x plus 1 squared. So if we think about this, using our current rules, the only way we can do this is 2 ways. The first would be to do this. before I take a derivative, I can do some algebra. I can notice that it's this, and then I can multiply it out. And when I multiply it out, I'm with 25x squared plus 10x plus 1. And then, of course, now I can compute the derivative because it's a simple polynomial. I'm left with 50x plus 10. And if I were to factor out the common factor, I could write this as, if I wanted to, I could write it as 10 times 5x plus 1. And so the reason that I'm going to rewrite the derivative is because what I'm looking for is I'm looking for a pattern. And so if we're very careful, let's put that here. So we say, is there a pattern? And maybe you do, or maybe you don't see it. I don't know. So let's up the game. Let's go to the next page and let's do another example. And I'm going to do a very similar problem. This time I'm going to say 5x plus 1 to the third power. Now again, I could use the product rule if I wanted, but instead I'm going to note that I can multiply this out using some algebra. So when you were in algebra class, you learned how to do this. You might have learned some tricks to multiplying these binomials out. And if you're multiplying these things out, you can do it the long way, which is fine. Or if you know the shortcuts, maybe you learned about a thing called Pascal's triangle or the binomial theorem. I don't know if these ring bells, but if you know any of that, or you just plug through the long way with all the algebra, what you end up getting is the following. You get that this is 125 x cubed plus 75 x squared plus 15x plus 1. I don't know if you guys are familiar with any of this or not. I don't know. But either way, you can do it the long way, or you can know the shortcut that I'm using. So if you want the shortcut, which you can Google is, so what I use to go from here to here is I use Pascal's triangle. I don't know if you know what that is, and what's called the binomial theorem. So if you want to Google that exact phrase, you'll find lots of good tricks how to do this if you want to learn. I was fortunate when I was in school. I had some good algebra teachers, and they taught us that. I don't even know if they still teach that or not. Okay. Nonetheless, no matter how you get to that, if you take the derivative, what you have is you have 3 times 125x squared plus 2 times 75x. And the reason I'm writing it like this is because what I'm going to do is I'm going to notice that this thing factors. This creature factors. Now, it might not be obvious to you, and that's okay. But if you ponder this, you'll say, okay, this thing could factor. I see that. I see, okay, yeah, maybe it does factor. And maybe you're good at factoring, and maybe you're not. I don't know. But nonetheless, what you'll notice is if you suffer through the factoring, is this thing can be written as, if you decide to factor it, is I can pull a 15 out of all these pieces. And then what I'm left with is I'm left with 5x plus 1 squared And you can verify for yourself this is true. Now, don't get worked up like I can't see this. Well, we're going to show you that what I'm doing now is a waste of time. There's a quicker, more efficient way. But the point I'm trying to show you is when I write my derivative like this, I might recognize there's a pattern. And perhaps if I write it like this, instead of writing 15 out front, if I write 3 times the quantity 5x plus 1 squared times 5, I might even recognize a pattern. So if we go back to the previous example, what I might do is I might rewrite, instead of writing this as 10 times 5x plus 1, I might get cute and write this as 2 times 5x plus 1 to the power 1 times 5. So let's summarize this real quick. I want to summarize this on the next page. And maybe you'll see there's a pattern. My technical difficulties. So the derivative, what we found is the derivative of 5x plus 1 quantity squared was 2 times 5x plus 1 to the power 1 times 5. And then we also found that if it was the power 3 instead, that we got this. So what you're noticing is there's a pattern. So what this suggests, and it turns out to be true, so this suggests that if you were to take the derivative of, say, 5x plus 1 to any power n, that this derivative would be n times this quantity raised to the n minus 1 times 5. So one of the things we love about mathematics is it's all about recognizing patterns and shortcuts and understanding general things. Now, I am not suggesting, as I said before, that maybe you guys as amateurs get this or see this pattern. You might be completely lost, and that's fine. It's okay to be lost, because when you're lost and then you work at it and figure it out, then you've learned something, and that's always good. So it's nice to learn things. But I hope you study these examples, because what we did is we suffered through algebra in those two examples. And then by suffering through the algebra, we recognized there might be a pattern. And then when we say there might be a pattern, what we do is we ask ourselves, well, holy, you know what? Is this a special case of a more general pattern? I mean, that's really what science and mathematics is all about. You study specific things, and then you ask yourself, how can you take what you learn about a specific thing and learn how that might tell us something about other things? I mean, you guys always hear me say that silly story about, you know, the first boat that was built wasn't a cruise ship, right? I mean, one day some person saw a log floating down a river and they're like, oh, you know what? Let's tie a few of these things together and we can float down a river. And then a boat was figured out. Right? I could cue the what about Noah's Ark, but then that's church and state and the same thing. We can't do that. Damn, I miss being in person. All the jokes we're missing out on being in Zoom. You're all sleeping. We don't even know if you guys are alive right now. You could just be just a little black box with a name. So sad. Anyhow, the fact of the matter is we suffered through a couple problems, and by suffering through them, we recognize there might be a pattern that can save us time, so we don't have to do this algebra. And that's really one of the things that mathematics is about. It's about recognizing structures and patterns and symmetries and being able to do things that normally would be a hard computation and figuring out a way to do it quickly. Okay, so does anybody have a question or a comment? So let's sort of rephrase it like this. So it turns out and the above formula is a special case of a more general rule for differentiating compositions. And so what is this rule? Well, the general rule says the following. Suppose we want to differentiate the composition of two functions. So let's remind you what that means. That means f evaluated at some other expression. So this is not multiplication, this is composition. So I'm throwing g into f. And so this general rule, which is called the chain rule, says you differentiate the outside function. You leave what's inside alone, so we leave the expression g alone. And then we multiply it by the derivative of the inside function. So this is called the chain rule. And it is usually one of the more difficult rules for students in Calc 1 to master. And part of that is because most of us at this level still have a hard time understanding what this composition is. But the fact of the matter is, many came before you and figured it out. You can do it. It's just going to require some work. So again, this is the rule for differentiating the composition of two functions. So let's look at an example of how we would apply this rule. And by the way, we're not going to prove it, but you could prove it using the limit and all that stuff. But it's more important that we see some examples, in my opinion. So let's look at sort of the way I would encourage you to think about this. Is how I learned it. Is I like to think about, when I look at this formula, I ask myself, okay, when I have a composition, I like to think of it as an inside and an outside function. One function here, f, is eating g. G is inside of f. So for example, if I go back to this problem, if I look here, these are compositions. The inside function is 5x plus 1. And then the outside function, the guy eating the inside function, is this power function. It's either power 2, 3, 4, 5, 6, power n. So a good example, in my opinion, to learning this rule, to really seeing what's happening is to look at this. Let's look at the derivative first of sine cubed. So the way you need to think about this, and this is what I would do if I were you, is I would ask myself, who is inside and who is outside? So in this particular problem, the cubing function is eating the sine function. So sine is inside, and the cubing function is the outside function. So the way you use this rule is you say, okay, great. So what's the derivative of the outside? Well, the derivative of the outside is 3 times input squared, and then it's the derivative of the inside function, which is the sine of x. So this is 3 times the sine of x quantity squared. And then we clean this up. This is 3 sine squared times cosine of x. So again, let me remind you of what I thought was helpful as a student when I was trying to learn this years ago, is here the outside function is f of x equals x cubed, and the inside is g of x, which is sine of x. So that's the way I'm not saying it'll work for you the way it worked for me when I was a student, but that's kind of the way I think about it. Does anybody have a question about this? Okay, now let's compare this with something that looks very close, but it's two different things. It's not the same. So if we look at this example, now I'm going to differentiate the sine eating x cubed. So I'm going to be, look at my grouping symbols. I'm trying to be very clear of what's happening here. So here, the outside is f of x equals the sine of x. And then the inside guy, who's getting eaten, the inside guy is g of x equals x cubed. And so the chain rule gives us a very efficient way of computing this derivative. It says you take the derivative of the outside, which is cosine, leave the inside alone, times the derivative of the inside. And so we can finally clean this up. This is cosine of x cubed times 3x squared. And typically we would bring the polynomial piece out front. That's just sort of most people's convention. And so we've computed this derivative. So again, lots of books have different ways of trying to teach you the chain rule. There's lots of great videos on the internet and YouTube and Khan Academy. Lots of free resources. And everybody kind of has their way of trying to teach this to you. This is the way that worked for me when I tried to learn it years ago. So that's the way I'm going to teach it to you. Now, maybe it works for you, maybe it doesn't. Does anybody have a question? All right, so let's look at another example. So let's take the derivative of the square root of x squared plus 10. So here the outside function is the square root function. So that's the derivative of the square root is 1 over 2 times the square root. So we'll do that. And then what remains is multiplying by the derivative of the inside. And so the derivative of that is just 2x. And so we can clean this up. Perhaps we might write it like this. Does anybody have a comment or a question? How do you get good at this? Practice. Practice, practice. How do you get good at hitting a baseball? You go find someone to throw baseballs at you and you swing the bat. How do you get stronger? You go to the gym and lift weights. How do you learn math? You do math. You don't watch other people do it. That's helpful. It helps you learn, but the sole learning, or the primary aspect of what makes you learn, is the practicing. It's putting in the repetition, so that these rules, you know, I always mock students, and I apologize if this mocks you, but I always find it comical when people study for tests by like memorizing flashcards. Like, that just seems to me to be the weirdest way to do something. You know, like, when you learn how to drive a car, you didn't like sit in your house and like just quiz yourself on what to do when you see a stop sign or a traffic signal or yield. You go out and drive, you learn. And then these things just become, the muscle memory is there. And so you don't think about it. When you're driving down the road, you don't say, oh crap, holy, you know what, there's a traffic light, what do I do? You don't pull over, get your driver's manual out of the glove compartment and then say, oh yes, this is what I do at a red light. No, you know what to do because you've done it. It's the repetition. And so I would encourage you not to try to memorize these rules. What I would encourage you to do is do practice, and then these rules become second nature to you. They're muscle memory. It's like riding a bike. It's like, you know, playing a sport that you've done your whole life. It's just part of what you do. It's ingrained in you. Now, the downside to that philosophy is that for most human beings, this is hard stuff to learn. Calculus is difficult to learn. It requires an awful lot of practice. And many of us just say, I don't want to have the time, or I don't want to dedicate the time to that. Like, I'm not going to be pretending to you guys. This is not easy to learn. Most human beings really struggle to learn this. I struggled. Most people do. There are very few people that can just pick up this stuff in 5 minutes. It's just not how it works. And here's another way to think about how challenging calculus is. Calculus was essentially invented in the 1600s. That means it took human beings thousands of years to figure this out. And we're asking you to learn what it took civilization a long time to learn. We're asking you to learn it in the summer in 10 weeks. So what we're trying to do. So you got to be very cognizant of, is that a word? I think it is. You got to be very, aware that it is difficult to learn this. And, that's just the best way I can explain it to you. So you got to practice. You got to do the problems in the book. You got to go on YouTube and watch examples. And you got to do the homework problems. And then you got to do them again, I always use these sport analogies and metaphors, but it's true. I mean, if you're practicing to be a soccer player, you don't just kick the ball once and say, oh, look, I kick a ball, I'm good. No, you'll suck. You don't get to play after Little League. If you want to continue and get better, you have to repeat. So I don't know. I feel like I'm screaming that from the mountaintops and you're all sleeping, which is fine. It's a holiday weekend. So anyhow, does anybody have a question, comment? So the last thing I want to leave you with, I think we'll end short today because, well, maybe you guys want to go have a picnic or something. You can celebrate. I shouldn't say this will be a good time in class when we're not recording for me to mock all the hypocrisy of history, but I can't do that because someone might say, oh, Grady is rude. He's mocking things. But do you ever think about hypocrisy? What do they say? The winners get to write history. Anyhow, go read a book after you do your calculus homework. Anyhow, so here's a cool fact that I'll leave you with before I get myself in trouble for offending you guys, or maybe I won't offend you. Maybe you're like, he's right. Hypocrisy is everywhere. Here's a cool fact. And we're going to see many ideas. So the chain rule can be used to derive many more useful identities. So we're going to leave you with one today, and then hope, you know, this stuff is hard to learn. So what I'm going to hope you do is I'm going to hope you do this homework 6, I believe it is. And because when we, on Tuesday, we're going to really start getting into how the chain rule can be used to get us all this information. So I hope that you'll have used this. I don't want to jump into that now because it's too much, in my opinion, in one day. So anyhow, one of these things is we can extend the power rule. To any rational exponent. So what do I mean by that? Well, we can use the chain rule to prove that the power rule works for rational exponents. That is, x to, let's say, we'll write it as p over q. And this sounds silly, but this is just p over q x to the p over q. So don't get bogged down with this scary stuff, but just look at a couple examples. What we're saying is that, for example, the derivative of x to the third is 1/3 x. We already know this works for negative integers, but now we're telling you it works for rationals. So the pattern is very, very nice. So I hope that you'll understand where these exponents are coming from. One thing I learned about students your generation is many of you aren't really good at fractions in your head, and that's probably because you guys spent most of your lives using calculators, whereas someone like myself, I didn't. But anyhow, I hope you guys will come to terms with the fact that 1/3 minus 1 is negative 2/3, and 5/4 minus 1 is 1/4. I hope you'll convince yourself that that's true. Oh, by the way, I wrote this wrong. Up here, this should be -1. Sorry about that. That was an honest mistake. Does anybody have a question about this stuff? Going once, going twice. All right, well then what we'll do is we'll hope that you practice this stuff, and if you have questions, you can email me. And again, do not hesitate to blow my email up. I think Elijah, you emailed me once or twice, and I think I responded, but I'm not sure. So you can email me again. I will not be upset at you. In the words of my father-in-law, the squeaky wheel gets oiled. So please email me if you feel like I am ignoring you or I missed an email. I apologize about that. And if you want your grades updated, scream and yell, and I'll hopefully get around to it. This is another thing I'm interested about. Like 5 years ago, we would have never thought to update grades. When I was in college, I didn't know my grade until 2 weeks after the semester ended, and I got a letter in the mail that said, here's your grades. But now you guys are so used to having instantly know your grades, and so I apologize that I haven't quite adapted yet. I will promise I'll get there. You'll probably all have higher grades than you expect anyhow. So, yeah. All right, any questions, comments? All right, well, thank you guys. I hope you have a good weekend. I hope you read some history and acknowledge all the good and the bad, and do calculus, and have a good weekend. I will talk to you guys soon. Thank you guys, and be safe.